Hey, welcome to The Explainer. Today, we're digging into the invisible blueprints that build our entire world. We are talking about the fundamental rules of connection that decide why some things shatter, why others bend, why some things flow, and others, well, they just stand firm. We are talking about chemical bonds.
So let's just jump right in with a bit of a puzzle. Have you ever really thought about salt, copper, and water? I mean, we see them every day, but why are they so incredibly different from each other? The answer isn't in what we can see. It's hidden in the connections we can't. To really get a handle on how things connect, first we have to understand the things that are doing the connecting. So we've got to zoom way in and take a look at the atom itself. For over 2,000 years, we basically thought the atom was just a tiny, solid ball. But then, as you can see here, there was this incredible burst of discovery that totally flipped that idea on its head. Now, the key takeaway for our story today is really what came at the end, this idea of a dense, positive nucleus at the center surrounded by this cloud of electrons. And it's those outermost electrons, those are the real architects of everything.
So it turns out atoms aren't just these passive little particles floating around. They are driven by a single, really powerful motivation, a goal that dictates pretty much all of chemistry.
And here it is, the octet rule. You can think of this as the golden rule of chemistry. Atoms are at their most stable, their most content, when they have a full outer shell of 8 electrons. This deep, fundamental desire to get that full octet, that's what drives them to interact and form bonds in the first place. This slide just shows it perfectly. On one side, you've got sodium, and it is practically buzzing with anxiety. It has just one lonely electron in its outer shell, and it is desperate to get rid of it. Then on the other side, you've got neon, cool, calm, collected. It's got a full set of 8 electrons, a perfect octet. It's completely stable and has zero interest in reacting with anything. So the big question is, how do atoms like our anxious friend sodium get to that stable state? Well, they have 3 main strategies to get that full outer shell. They can give, they can take, or they can share electrons. Let's see how that all works.
All right, our first strategy is the most direct. One atom simply gives an electron away, and another one is more than happy to take it. I like to call it the Great Electron Heist.
Okay, picture this. Sodium needs to lose 1 electron. Chlorine needs to gain 1. It is a perfect match. So sodium just transfers its electron right over to chlorine. Now here's the cool part. Sodium is a positive ion, and chlorine is a negative ion. And just like magnets, those opposite charges attract and lock them together. That's the strong ionic bond you find in simple table salt.
Okay, but what if neither atom really wants to give up an electron? What if both of them need to gain one to be stable? Well, if you can't get what you want by taking, you cooperate, you share.
Water is the absolute perfect example of this. Oxygen needs 2 more electrons, and each of the 2 hydrogens needs 1 more. So they make a deal. They share their electrons. And this way, every single atom gets to count enough electrons to have a full outer shell. It's a total win-win situation, a cooperative masterpiece that creates, one of the most important molecules on the entire planet. Now, metals, they have a totally different approach. They're not really into these one-on-one relationships. Instead, they go for something that's way more communal. In a metallic bond, all the metal atoms toss their outer electrons into one giant, shared sea of electrons that just flows freely between all of them. These electrons don't belong to any single atom anymore. So you have all these positive metal ions held together by their shared attraction to this negative sea. And that free-flowing current, that is precisely why copper is such an amazing electrical conductor. Okay, so now we know how atoms connect. But believe it or not, that's only half the story. To truly understand why water is a liquid, for example, we can't just look at the bonds. We have to look at the final 3D shape of the molecule. It's called VSEPR theory. And yeah, that name is a mouthful. It sounds super intimidating, but the idea behind it is actually incredibly simple. Electrons are negatively charged, right? And things with the same charge repel each other. So all the electron pairs around an atom are just going to push each other away until they're as far apart as they can possibly get. That's it. That's the entire theory. And to really get this, let's just forget about electrons for a second. I want you to just picture tying a few balloons together at their knots. So if you tie 2 balloons together, what happens? They'll naturally point in opposite directions to get away from each other. That's a linear shape. Tie 3, they'll make a flat triangle. 4, they'll pop into a 3E pyramid shape. Now these balloons can be the electron pairs that are forming bonds, but
And this is a key point. Some atoms also have pairs of electrons that aren't bonding at all. They're called lone pairs. But they still take up space and they still repel everything else just the same. So all these groups push each other apart. And in doing that, they define the molecule's final 3D shape.
Okay, time to zoom back out. We've gone over the rules, the octet rule, the 3 bonding strategies, and this VSEPR theory about shape. Now, let's connect all these invisible, microscopic rules back to the very real, tangible properties of the stuff we started with.
And this is where it all just clicks into place. That rigid, repeating ionic bond in salt, that's what creates a hard but brittle crystal. That metallic sea of electrons in copper, that's what lets it bend without breaking and conduct electricity. And water is the really interesting one. The oxygen atom is bonded to 2 hydrogens, but it also has 2 of those lone pairs we just talked about. All 4 of those electron groups push each other apart, which forces the molecule into this specific bent shape. And that bent shape is what lets water molecules stick to each other so well, making it a liquid with that amazing surface tension.
So the whole point is this. A few incredibly simple rules of giving, taking, sharing, and repelling are responsible for the amazing, wild diversity of the entire material world, from the salt you put on your food to the wires inside your walls. So the real question is, now that you know the rules, whatever the object, will you never see the same way again?